Well, in the previous class, we completed our transformer architecture, and in the transformer architecture, that was one of the successful architectures, and it was considered as a breakthrough in natural language processing, and it gave an inspiration for the research which is now ongoing in LLMs. Okay, so there was one thing in decoder I told about teacher forcing. Okay, and in teacher forcing, that is decoder, it have an idea or knowledge what to produce. However, we are masking the next tokens in attention mechanism. Okay, I told in the previous lecture that our model is trained model on huge amount of text. So if you do a query to it, it will collect the response from its knowledge, and it will then produce the output for you. This response collection, as we have seen in decoder, that because the transformer architecture is basically for translation. Okay, so the English words which we have taken, they are translated in French. Okay, so what could be the French words? It do have an idea. We are not saying that our architecture is absolutely blank. No. However, there is a proper mechanism to produce an output. It doesn't mean that if you know something that you have to give that same as an output. No. The French words are tokenized, then mask attention mechanism is applied over it. We don't want our model to cheat. There should not be like an prior information that after this term will come. No. I told in my previous class also that first I will teach you, then I can ask you a question. Okay, so I teach, you do have a knowledge about what has been taught to you on a particular topic, then I can ask a question on that particular topic. So from your knowledge, from your database, you will produce an answer. Similarly, here also in teacher forcing, it picks up your words from according to its knowledge, what it has learned, then tokenization, then mask attention, then linear layers, then softmax. Finally, you are going to get a result. Okay, so you should be knowing about this teacher forcing in transformer architecture. Okay, fine. Now let me share my entire screen. We were discussing about BERT. So BERT, we have studied the concepts related to it, and the transformer architecture I picked because of BERT only. Bidirectional encoder representation from transformer. Actually, na, these concept came because there was an issue related to sequential models. That too I told, like RNN and its cousins. So this mechanism of transformer, which provides you a flexibility of parallel processing with attention mechanism, helped a lot. Okay, so BERT is bidirectional encoder. That means you already know we process our text from both the directions. The idea is to understand the context in a better way. Okay, so developed by Google, able to handle complex representations in the data. Okay, many things we have already covered in the BERT, and the working also we have studied in the previous classes before transformer architecture. Okay, so here is what we do in BERT. As per a recall, we take 85% of the data for the training, and 15% we perform masking. Okay, so by training only, my model will understand what word should I substitute in mask. Okay, so here are certain tokens like classification, how are mask doing today. Now BERT has to decide that which word I need to put here, and this is separator or a full stop. So after giving this sentence into the BERT, the BERT will decide which word is having the highest probability of substitution. Okay, so to have a small recap, it is neural network architecture only. See, transformer are neural network architectures only. They do have self attention, and now you are very good in self attention. Fine. The context awareness used in the BERT gives ability to generate the word embeddings on the basis of context. If we consider a sentence, the lead singer will lead the band. That means it will understand what the word lead means if it process from the left to right to left. Okay, because the word is same lead, but the meanings are different in what context they are used in a sentence. That is why we are taking it as bidirectional. Okay, fine. So the BERT process your input in this way and produce the output. Okay, and I also told you that tokenization we have studied in BERT. Word piece tokenization is being performed. Okay, I do have a code for it. You can see this is a BERT code. Okay, I think I have shown previously also. So you need to import the BERT from transformer. Okay, so this is BERT tokenizer. From transformers, import BERT tokenizer. Then you have to take BERT base uncased. See, base, this is the base model. Okay, there are various versions of BERT. It comes under a category of large model. So we do have different versions. So this is the basic model. Case and uncase. There are two things. Okay, whether your model is case sensitive, whether your model is not a case sensitive. So here it's going uncase. What does uncase means? Uncase means that your model will ignore whether it is an uppercase, whether it is a lowercase. So that is what called as an case sensitive. It ignores. Fine. So that's what uncase means. It's up to you. You can take case sensitive also. So what you have to write here is BERT base case. So if you take case sensitive, fine. Right now I'm taking BERT base uncased. So it doesn't matter you are writing in uppercase or lowercase. I gave a text BERT pre-processing is essential, and I want my BERT model to tokenize it. And here I am printing the tokens also. So you can see the tokens which are printed. These are word piece tokens. What we are expecting is, okay, this is your text. So the tokens could be like BERT, comma, pre-processing, comma, is, comma, essential. This we are expecting. But word piece tokens are like this. BERT, comma, prep. Okay, then hash hash RO, hash hash CES, hash hash SING is essential. So word piece are tokenization within tokenization. That means it is considering sub-word tokenization. Okay, it is further breaking down the words into smaller units, more small units, to handle the vocabulary problem in language models. See, it's not like that model can understand everything, whatever you give as an input. No, we have to give an ability to the model to understand each and everything. And the ability will be depending upon how twist can be made while giving an input. So server tokenization will, if it is possible, it can break that particular word into further tokens. That's what it did with pre-processing. Okay. So instead of treating each word as a unique token, WordPress splits the words into smaller subword units. These units are the parts of word appear frequently in the training data, help to reduce the vocab size. Okay, one more thing, very much important. Now again, from where this concept came, you can understand, and we very well know about in natural language processing, when we also do the project, if you remember, we perform lemmatization. What happens in lemmatization? We take the root word. Okay, for example, if I say writing, so the root word of writing is write. Okay, we are having playing, played. So the root word of playing and played is play. So it is saying that it may happen that you may have similar kind of words. So if we consider the similar kind of words as individual token, then the vocab size will be huge. Playing will be another token and played will be another token, so vocab will be more. So obviously processing time will be more for your model. So what I did it, that means subword creation is it is performing lemmatization. Okay, so pre-processing, you can see pre-process. See, that's what it told, na? Here, vocabulary. See, there will be vocab construction, and I already told you what is vocab. What is vocab? The vocab is conversion of tokens into integer. Okay, so if I say my name is AI, so if the tokens will be made like this, my comma name comma is, and if I'm going to create the vocab, I will annotate these tokens with integer value. This will be called as a vocabulary. Conversion of tokens into integer notations. That is called as a vocab. Okay, fine. So it's saying that vocab will be more if you don't perform this activity, because the next will be embeddings. And we have studied in concrete about, because you need to do the embedding. Embedding will be word embedding and positional embedding. That's what we have learned in transformer architecture. That means these are the vectors. Okay, so things don't get complex, and we want to keep them simplified. So that's why it's been done. Okay, and there are some OOV words also. That means the word piece can break down the words into smaller units. It can handle unseen or rare words during training by splitting them into meaningful subwords. That's what it can do. However, there are some words which are out of the vocabulary also. Okay, so it can handle. However, it will tag them with OOV. If any of the word which is not been in understanding of the LLM, it will mark it as OOV, out of the vocab. Fine. It will try, it will put every effort to understand what you have given as an input. Okay, something wrong type or whatever. Okay, it will create the word piece tokens and everything. It will understand. It's not in like a simple system. Okay, it's a complex system. Fine. So here you can see I am learning word piece. So I am learning word hash hash piece. Full stop. So word piece is split into tokens, word and hash hash piece, because piece alone is rare in the vocab. But word and piece are common. Okay. So piece is rare. It is rarely been used in the vocabulary. Word piece are the common term. Okay, so it splitted this particular word. Okay, so my model will able to understand in this way by splitting. Okay, you are now, because seeing the implementation of the BERT, how to use it. It comprises of 12 transformer block, 768 feature dimensions, 12 attention heads. Vocabulary size is 30,522. So this much words, this much tokens it can have, and maximum sequence length is 512 tokens. It can handle 512 tokens. While in case of sequential model, the sequence length is less. The bird can take this much sequence length, 512 tokens. Okay, fine. Now, if you give an input sentence, I love apple, it doesn't mean here to split. There is no chance to split I love an apple in piecewise. That's not required. So, where it is required, it will do. Where it is not required, it will not do. Okay, got it? Fine. So, this is tokenization actually. This is a tokenization process. Okay, here are the tokens. Okay. So, the word base uncase use word piece tokens. Okay, fine. Also, if you want to perform classification with the BERT, so you can use this part of code, like from transformer import BERT for sequence classification, BERT tokenizer, import torch, which is your framework for deep learning, and you take tokenizer also and you take model also, both you can take. Okay, both you can take. And then, okay, here is your model. BERT for sequence classification from pre-trained. So this is a pre-trained model, and this is also a pre-trained model. This is for tokenization, and this is for classification. And then you can give your text as an input. The movie was amazing. So tokenizer, okay, first you have to tokenize this sentence. Then you have to give input to the model, and model will produce the output. Okay, model will produce the output. Now what actually it is? See, uh, these are the models, as I already told you. BERT for sequence classification, it's a pre-trained BERT for sequence classification task. Okay, like text classification for positive and negative sentiment, spam or ham detection. So we have done projects also related to text classification, and text classification comes in many forms: positive sentiment, negative sentiment, neutral sentiment, spam, ham, and many tasks can be there for classification. Tokenizer, I already told you that we do tokenize and word piece tokenize the words, and it take the special tokens like CLS and the separator. So one is the classification token and one is the separator token. Okay, it takes these two tokens. All right, fine. Here you have loaded your pre-trained model that I already explained. Okay, it is uncased, and here you have loaded your cased model, uncased model. Sorry. Okay, so it will also not consider what will be the case of the input. Okay, because it is BERT base uncase. Fine. And then you gave a text as an input here. This movie is amazing, and then you perform the tokenization of it. Fine. So the tokenizer will convert the text into tokens, and it performs the following step. It will add classification token in the beginning, separator token at the end, and it convert the tokens into ID based upon the vocabulary that is called as vocab. I already told you that this is the integer annotation. It will annotate your tokens into what? Integer representations. Fine. And return tensor.pt means it return the tokenized input as PyTorch tensors. Okay, with tensor, like in a form of a tensor. That is high dimensional representation of the data. That's what it will share. So this is compatible for the BERT to interpret, because BERT expect tensor form. Okay, so tensor is high dimensional data. Okay, and then you are going to give this input, the tensor input, into the model for interpretation. So you are going to pass the tokens to the BERT model. The BERT uses its architecture, and it produces the output containing logits. Okay, logit. Logit means it will give you the probability. Okay, between 0 to 1. Okay, logits you very well know, logistic regression, because it's a classification now. So if you're doing binary classification like positive or negative sentiment, so it will give you the output accordingly. Fine. So binary classification, positive, negative sentiment. There will be two values for the logit, one for each class. It may happen that the movie was amazing if it is having positive sentiment. Okay, so high probability for positive, low probability for negative. Okay, that's what it will represent. Okay, and here you can extract the predictions. So extract the logits from the model output. The logits are raw prediction scores where each value corresponds to a class. Okay, So for binary classification, we are having this shape of the tensor: batch size comma 2, one value for each class. Okay, and Rmax, it's not new to you. Previously also we have used the Rmax. Okay, so it will pick up the index position where the value is present. So it will find the index of the maximum value, argmax. That means the value present at the maximum value present at the specific index position. It will pick up and it will return that particular value. Okay, that is the highest score, index of the highest score. Okay, and specifies the dimension one specifies RMS operation should be done across second dimension. That means the input it picks the class has the highest logic prediction. That's what it is saying. Okay, it will pick up the class which is having the highest logic prediction. That's why it's saying dimension one. Argmax operation should be done across second dimension. That means classes. Second dimension classes. That means we are having binary classification now. So in regards to that only, it is writing dimension one. Specify the RMS operation should be done across the second dimension classes. How many number of classes we are having? Two, positive and negative. So they are writing dim equal to 1. Okay, the things starts from 0. Okay, so that's the reason. Because in binary classification, the Rmax will return 0 for the first class and 1 for the second class. And this is arranged in ascending order. So I'm going to have the second class because its probability value will be more. So I'm going to pick up that value. So RMS will pick up the index where the maximum value is present, and that will be the second dimension. Okay, and you can print the prediction. 0 could be negative sentiment, 1 could be positive sentiment. Could be. Okay, not sure. Okay, so you can print the predictions from it. Okay, fine. So this is the basic code of BERT. Okay, so in implementation, what we have seen with BERT tokenizer, you gave input, okay, to the model. And what model has? Model has tokenizer and classifier. We do have two separate pre-trained model. First, tokenizer tokenize your input. It will create tokens or word piece tokens. Then these word piece tokens are converted into vocab. Then vocab is converted into tensor. Tensor is a high dimensional data. Obviously, ये tensor representation will be like it's a representation, and this representation is expected by the transformer. Okay, certainly we can talk it as embeddings only. It haven't clarified it as embedding. It called it as tensor as per the code. It's mentioned .pt. So that is what expected by the encoder, because in encoder there will be attention mechanism, and what we have seen in the attention mechanism, we give the vectors. Okay, so the representation of any value, if it doesn't have any, it's a simple, then it's a scalar. 2 I cap is vector, then 2, 3, 4, 5 is a matrix, and 2, 3, 4 5, 7, 8, 9, 10, 11, 12, 13, 14. That means matrix inside a matrix will be, it's a high dimensional data, then it will be called as a tensor. That's what I teach in my machine learning also. So scalar, vector, matrix, and tensor. So it told that tensor is required. Okay, so there will be like so many word embeddings. It will be converted into tensor representation, and that will be given as an input. And then classifier will perform its task for the classification. Classification, it told that okay, if it is positive or negative sentiment, I will give. Okay, you do not have to do anything. My work is classification. I am BERT classifier, so I can do that. And it's based upon logits. That is why machine learning is important. At least you should know the basic logits. And it will organize the things according to the index, and it will return the index. It will return the highest probability. Okay, that's what it will do. Now, wherever the highest probability is present, zero may be like, it's saying that zero may be negative, one may be positive, zero may be negative, but I'm just have a doubt related to it. See, argmax, argmax, that means maximum value it has to return at whatever be the index position it is, and and for example, what we do, see, the output will be like, if it is arranged, if it arranged like 0th index position, 1th index position, it say that this is 80% and this is 20%, zero point 0.8 and zero point 0.2. Okay, zero point 0.8 and zero point 0.2, for example. Okay, I think it put a notation also. 0 means positive, 1 means negative, and your text was the movie is amazing. So amazing means it's positive sentiment. So it will return the value which is present at 0 index position. Okay, how much it is? 80%. Now 80 means positive. So it will return positive. It will say positive. And if I say I didn't like the movie, I didn't like the movie, then what will happen? I didn't like the movie, then here it is 80% and here it is 20%. Then this is negative sentiment. This is positive sentiment. This is 0 and this is 1. Then it will return negative as an answer. Now this will be the highest index. Okay, so it will select a dimension. It return something like dim equal to 1, dim equal to 1. The thing is, it's going to return one dimension. Return one dimension. Where is the highest value present? Just return that. And we are checking the highest value presence at the index position by argmax. That's what we are doing. So whenever you give as an input, it will consider, it will add the tokens from its own side like CLS. Then the movie is amazing separator. This is how it proceeds. Okay. So you have to indulge your learning in this token. Okay, you have to go through more about it. Token embedding, word piece tokenization. Okay, the basics of NLP are very much required to study. If you understand the basics of NLP, then only we can grasp this concept thorough. Else, it is something a bit complicated. However, I tried my from my side that to make the things easy, and now it's up to you. Okay, so Input format, you very well know. Masking, I told you. Okay, once you trained your model with 85% data, then 15% you can perform the mask. Okay, during training only we perform mask. It's not like that after training you are, no, no. During training only. Some of the words are mask. Okay, and this is the code snippet we have seen. Okay, fine. All right. So, acha, we can fine tune BERT for specific task. That's also it's possible. We can fine tune BERT for specific tasks. That's what we did. Okay, like sentiment analysis and all this thing. Okay, we can fine tune the BERT for that. For example, you are available with the data set. Okay, and I have a problem statement of hate speech classification. So you are having a text and you are having a label. These are the text and this is a label like hate or non-hate. Hate or non-hate. Okay, so this will be considered as a downstream task and I can fine tune BERT model to perform this task. Fine tuning, I explained you. In fine tuning, you are going to adjust the weights of the model of the model. That's what you have to do in fine tuning. In transfer learning, you don't do anything. You just take the weights from the existing model, pre-trained model, and you just add further more layers. Just take the weight from them, and the training goes on here with the weights which I am available with from the pre-trained model. But in fine tuning, you adjust the weights of the pre-trained model. Okay, that's what we did. So, huh, architecture variation I already told. Bird base, bird large, and there are many more. You can check out the Hugging Face library. Okay, or you can check the official website of Hugging Face. There you will able to see BERT and other large models. Okay, all are present in different versions. Okay, fine. Here also the code I have mentioned. It's clear to you. Attention mechanism, it came and we have done a lot on attention mechanism. Self attention I explained, multi-head attention I explained. Okay, so bird's attention isn't limited to just the word before or after a word. It consider both the directions. Obviously it's bidirectional encoder. Okay, BERT generates embedding that consider the entire context of the word. It's understanding. It's like understanding a joke, not just by a punchline or just give a setup. See, we have already seen the entire architecture of transformer, and it took a lot of time for me also to explain you each and every component. Okay, so obviously it's not a joke. Okay, we are making a machine to understand something and producing an output. It's not at all a joke. Okay, however, now we gave so much capability in the machine that it can perform such tasks very well. Okay, so this here is the code to visualize the attention weights. You can take BERT model, BERT tokenizer. You can take BERT tokenizer pre-trained. You can take BERT model pre-trained. Okay, and then you can give a text as an input. BERT's attention mechanism is fascinating, and you can give this text as an input to the tokenizer, so it will convert it into tensor. It will perform the padding if it is required. It can perform the truncation also. Then you give this input to the model. and it's saying that output attention, that which word is important. Kindly print the weight, print weights, which word is important. So output attention true. So it will give you the output, it will print the weights, attention weights. That also you can check. Okay, fine. So I will be doing this code also and I will be sharing it. You can practice. It is very much important to devote some time and understand that how the LLMs are working. Basic mechanism should be thorough to you so that you can answer in interviews also. So BERT training process. Okay, we have studied this thing in previous tutorials of BERT. MLM, that is masking and next sentence prediction. Both we have seen. See, pre-training phase, that means journey begins with pre-training. It learns the enormous amount of data. Okay, that is the reason it can produce something. It already have an enormous amount of data learning. Now, once it know, once it know, it is having already a knowledge. That's what it is saying. But millions of sentences. Imagine showing Bird millions of sentences and letting it predict missing words. It can do that. So in the transformer also, in the decoder, in teacher forcing, when I started my class, I told that it is having knowledge. Now the thing is, it has to produce the output. What could be the next word prediction it is going to do? So from that knowledge only, now, and we are not by masking we are preserving it to do cheating. Okay, so it is having an attention matrix plus we will add a masking matrix, and the next word prediction will all become zero probability, and then we are giving this to the attention mechanism, next attention. You have learned everything in transformer architecture, so it will try to fill in the blanks. That is the game. It will do. Okay, and next sentence prediction also we have seen that 50% you are going to give the correct, and 50% you are going to give incorrect. Now it is responsibility of the bird to understand which one is correct and which one is incorrect. This is how the training goes. Okay, it will try to connect that, okay, after a sentence, this sentence will come. Okay, so LLMs are capable enough to. Okay, it's not like that if I ask a question, explain AI, it will write one line of AI and then it will start explaining science. No, it doesn't happen. Whatever you are asking now, it will produce the result, it will produce the tokens and everything. Next sentence to next sentence, it will do the same. Okay, so here in pre-training, just see from transformer import BERT for mask LM and BERT tokenizer. Okay, BERT for mass LM. Okay, so mask wala we have taken. Then it is again uncase wala train karna hai. So we are taking this, okay, the tokenizer and the model. We are taking BERT based uncase. Okay, and then we are giving a text. BERT is a powerful language model. We are performing the tokenization of it. Okay, and then we are giving a model to see what will be the output, and we are producing the output here also. So what exactly happening here? See, the code demonstrates the pre-training of the BERT mass language. Okay, that's what now it's called, BERT for mass LM. That means BERT for mask language model. Okay, so BERT is also having different forms. Previously, you took BERT for sequence classification. Tokenizer is common. Tokenizer is common. and the things start from tokenization only. Here you perform masking. Okay, this model will predict the mass word while being trained to minimize the prediction error. So BERT's training process is like teaching it the rules of language through mix of fill in the blank and the sentence pair understanding. That's what we do. Okay, we just give the things in combination. Some are masked, some are unmasked. Okay, sentence prediction also. So this is how we train the LLMs. Okay. So the first thing is, it's like, okay, the first thing is you take the huge amount of text. You take huge amount of text and with unsupervised learning, you give it to the model. That means you're feeding to the model. Okay, whatever be the data from here, there, and whatever you feed it to the model, take it. Okay, and then okay, you perform fine tuning also. Then you perform fine tuning. That means if this is the input, this will be the output. This is how you perform the fine tuning. Currently, what it has been told to you in the BERT uncase LM, mass language model, BERT last mass language model, what it has been told to you that it's a training process. In the training process, we perform masking of some words during training only. We perform the masking of some words. Along with that, we are expecting NSP, next sentence prediction. So we give a pair of good sentences. We may give a pair of bad sentences. Bad sentences means after this sentence, this will not come. So this is good pair and this is the wrong pair. It's responsibility of the model to understand whether it's correct or not. So this is what it do in BERT. So we do have the embeddings, word embeddings. I already explained you word piece and everything. I do have certain basic codes, elementary codes for you to understand the BERT. And there are various versions of the word like Roberta, Albert. Okay, that is a light BERT. There are many versions. Okay, Distilbert, Electra. Okay, so there are these versions. That means they are upgraded BERT versions. Okay, you can check them from the Hugging Face, that website, and you will get all these versions. Okay, we can take these versions also for our understanding. However, it is requested for you to go through the architectures for them, and we can check the basic codes how they are producing the output. Okay, that's all we can do here in BERT. Fine. So you understood the class today or not? Please tell me. Have you understood the concept? Okay, fine. Let me stop
Yes,
presenting.
yes, sir.
All right. Let me